Oh. Is it on there? Okay.
Okay, great. I really hope you all can hear me well. My name is Kapeliukha, and I work as, closer here. Oh, I'm sorry. Okay, closer to this microphone. So my name is Kapeliukha, and I work as the head of machine learning at ChemSpace. And today I would like to talk with you about creation of ultra-large chemical spaces, specifically with the help of machine learning-based reagent filtering. And also, we're going to talk about some cool tricks, how you can explore such large chemical collections with the help of RDKit. But at the beginning of this talk, I would like to take you, on a slight journey into the chemical space, but we're not going to talk about the 10 to the power 60th stuff because you're cheminformaticians, you already all know that. But we're going to go to the part of the chemical universe which contains ultra-large chemical spaces. And there are numerous examples on the market. Some of them are open source, some of them are proprietary, but there is just something that all of these have in common, and this is their synton-based nature. For the ones who haven't worked with combinatorial chemical spaces, syntons are created from building blocks by replacing the functional groups with the reaction handle. These syntons are then combined together in different combinations to form the so-called chemical space. And this synton-based nature is actually a very cool trick that we as cheminformaticians can use to develop specific applications that will be super efficient to explore such chemical collections. And this is something that we're going to talk about slightly later in the presentation. Inum Real currently is probably one of the most explored commercially available chemical spaces. This graph was actually stolen from one of their recent LinkedIn posts, so I'm not the one who made that. But you can see that last year it was cited in almost 120 publications. This is kind of a shout out to their marketing team, but this is also a great proof that such compound collections can be used for heat identification and heat expansion stages quite efficiently, because if people didn't find anything there, they wouldn't publish papers on that, of course. But why this space and why people are actually using Inum Real? And this is because they pretty much attempted to solve the problem of synthetic accessibility. And people who use this space, they know that they're going to get their compounds at reasonable price and within roughly 80% synthesis success rate. And the synthesability aspect is actually very important for all kinds of combinatorial spaces because you can enumerate a lot of things, right? Sky's the limit, imagination is the key. But after you actually use this space, you find your virtual hit inside, and then you actually have to make it, right? In the lab to test it and to see how your computational workflow performed. And then when you cannot get this molecule synthesized, this becomes a problem because you pretty much did your work for nothing. But with all kinds of problems also come potential solutions. And one of the solutions is experimental validation of reagents. This is the approach that Inum is using for their space. So what they're doing is pretty much taking the building blocks that are candidates for a specific reaction. They validate them in the specific reaction protocol and check if that building block performs well. This is probably the ideal way to approach this, but it is also quite long and expensive. So this is a big investment upfront into that validation of a reaction. And it is not really applicable to external chemical collections because why would people test building blocks that won't make them profit, right? Another approach to do that is computer-assisted synthesis prediction. And for me, this is probably one of my favorite fields to look after because there is a lot of amazing work that is done in this field right now. But it is also a bit limited by the presence of training data, especially in the open source domain. So this limitation leads to the models having not optimal performance and sometimes not good generalizability. And also, if we're speaking about ultra-large chemical spaces, it also requires a huge computational expense to run inference on multi-billion or even trillion-sized spaces, because the models used in this field are usually the harder ones like transformers and stuff. So when we looked at this problem, we thought what we can do about it, right? And the solution that came to our mind was actually to try to filter the building blocks prior to enumeration of the space using ML models. So pretty much we recreate the experimental reagent validation, but we use it with the help of ML. Even though we do know that this method is not 100% accurate, and nothing is 100% accurate in ML, and if it is, then you're doing something wrong, but it also has quite cool perks to it. So this method does not require full enumeration. So you're not working with billions of molecules, you're working with thousands or tens of thousands, which is much more pleasant. And this makes the predictions very cheap. So you can not only do cycles of experimentation and look how your models perform in production, but you can also use this information to add additional cycles and no additional expense. And you can also apply these models to external collection of choice. So for example, if some new building blocks come out and your model is able to generalize to those, then you can also use them to update the space as new collections become available, and it doesn't cost you additional resources. When we came up with that idea, we came to Inamin and asked if they could provide us with the data that they obtained during their experimental validation, and they kindly said yes. So this is how we obtained not only the data for the validation, but also the statistics which was obtained during the years of operation of Inamin Real, so the kPaus that they synthesized within this space. And this data was manually curated, so it was a pain to clean up, but it was a very interesting challenge. But we ended up having data sets that contain anywhere from 1,000 to 20,000 data points. And you can see an example of such data set on the slide. So this is dummy data. It's not like real records or anything. But for example, if the building block participated in 20 reactions total, and out of the 20 reactions, 18 were successful, this means that this building block is suitable for this transformation. And here it is important to understand the meaning of success in this case. So it doesn't only cover the presence of the product in the reaction mixture, as it is usually recorded during high throughput experimentation. It also covers purification of the final product and the obtaining of this product in 90% plus purity via LCMS. So this data set implicitly accounts for the problems that can be faced during purification. So after we prepared the data sets, we started trying to model them, right? And our first attempts were to actually use only syntons to represent the building blocks that were going to go into the space. But we quickly realized that though this approach somewhat works, it is not 100% correct because there are building blocks that will have the same synton, but different functional groups. And for example, the ones that you see on the slide right now, they will have very different reactivity depending on the reaction they are used in. So this is how we came up with the so-called synton building block molecular representation, which is pretty much a disjoint graph that features both the building block and the synton and gives the model additional information. What we did is then we fed this information into ChemProp and we used it to train our models, and the models were designed as binary classifiers, and they pretty much predict how suitable is the specific building block for a given reaction protocol. For you to visualize it in your head better, there is an example of processing of a single reaction. This is an example of an amide coupling. And you can see that for each reagent type, so we have separately amines and we have separately acids. We have two different models that are tailored to a specific building block class. So after we perform this filtering, we take the compounds that passed the filter and we perform their enumeration. And currently on this slide, you can see the full ML-assisted space generation workflow. We're using this workflow to create our spaces, but it is also quite general and expandable, so it can be used to create custom spaces pretty much from any given building block collection. So for our space, we first formed the building block collection based on the in-stock building blocks that we had in our catalog. And we applied cutoffs based on price and lead time so that it is economically reasonable to include the building blocks in the synthesis. Then we created the building block pool types. using the smarts patterns that we created for every single reagent in every single reaction protocol. And then we filtered them with the ML models. Currently, this workflow supports 40 different reaction protocols, which is 29 distinct chemical reactions, and it includes 2 and 3 component reactions. The here link doesn't work here, but the slides are in Discord. So if you would like to see the full list with schemes, you can just go there and check it if you'd like. This workflow was benchmarked on Freedom Space 3, which we launched a few years ago, I would say 2 years ago. And we have been collecting the statistics for orders that were placed through ChemSpace for Freedom Space 3.0. And you can see the general graph of 10 random orders on the slide. With all of our statistics that we have, the experimentally confirmed synthesis success rate is 81%. But you can see that for some orders, the success rate is higher than for the others. And this is easily understandable because usually the compounds that are ordered by people are biased towards their specific selection protocol. So some of them are located closer in the chemical space. We're still continuing to collect the statistics, and as soon as we have more, we will be happy to share that with the community to further validate this approach or maybe unlock some limitations that we could possibly face. But what was interesting, and this is kind of a bit of an inside information, that in the Freedom Space, we had 3 human filtered reactions and 7 ML filtered. And we were kind of suspecting that the ML filtered will perform slightly worse than the ones that filtered by actual human experts. But it was not the case because the reactions had actually comparable performance between the ML and the human filtered ones. And also on the slide, you can see examples of some order timelines. So this is needed to showcase that the lead time that we advertise for 5 to 6 weeks is actually something that indeed happens, and people get their compounds synthesized within the marketed timeframe. And with that, I would like to summarize our Freedom Space 4.0, which is a combinatorial chemical space of 142 billion molecules, which was created using 40 ml filtered reaction protocols. We have the synton-based version of the space, but also we have 2 enumerated subsets. The first is the rule of 5 enumerated subset, and the other is beyond rule of 5. Why we did the beyond rule of 5, and it has more interest from the community from what we see, is because the targets are becoming harder and harder, and we see the need from the community in larger molecules. And we see that people downloaded it more, actually, which is interesting. That kind of showcases the latest trends. Now we're coming to probably my favorite question that people asked me on conferences a lot when I was presenting the poster on this. So what is the difference, right, between the real space and the freedom space? In the short answer, there is difference. But the serious answer is that the freedom space was designed to be complementary to InMinReal. This means that it is designed to be an additional source of compounds because these compounds are slightly more expensive. And we included the building blocks that are shared between the 2 spaces on purpose, so that if you do hit expansion within InMinReal and you don't find good follow-ups, you can try your luck and find additional molecules within freedom space for hit expansion. But you can also see that it occupies quite a lot of distinct chemical space, which can be used for the hit identification strategies, like additional compounds for that. And also from the UMAP, I know that 1 million is probably not very representative of such large space, but that's what we can do with the power we had, that the real molecules are slightly more diverse. And that is the result of the fact that there are simply more reactions, and we are actively working on adding new ones to the freedom space as well. So here are the access options. So you can get the enumerated subsets. You can also search the space through different softwares like BioSolve and LFRON, and also within the ArcticKit library, which is we're going to talk about in the next few slides. And because freedom space stands for freedom to explore, we are happy to provide the raw syntons and reactions files to everybody who's interested in them, especially if you're working on some synton-based developments. Actually, there is a very handy QR code. If you scan it right now, it will pop up an email with everything filled in, and you can just send it to our managers and they're gonna figure out everything. It's absolutely free. You'll just need to sign a licensing agreement for the Synton. And also, another thing we did to simplify the access, especially for less technical people, to Freedom Space is the Freedom Search platform, which is actually working on the RDKit Synton-based search. So the platform currently supports single and multiple queries, and you can also draw your molecule that you're looking to search for within the sketch window. And it currently supports exact match and substructure searches. We are actively monitoring the usage of the platform, and if it becomes quite popular within the community, we're planning to add similarity search as well. And also we're looking into adding tailored subsets for different tasks, like for example, diverse selections for docking, machine learning inference, covalent subsets, and things that could be used either as benchmarks or as reasonably sized sources of chemical compounds. When you submit your query, you'll have to input the email. We're not going to use it for anything. It's just there for us to be able to send you the results. And here are the columns that you're going to get for your query compounds. And it outputs up to 10,000 molecules per query. If you need more, you can contact us and we can figure something out together. And the third part of the presentation is actually we did some benchmarking of the RDKit Synton-based search together with David Cosgrove, who was the implementer and developer behind this algorithm within RDKit. There is a QR code to documentation if you want to have a look at it while I'm talking. But with that, I want to name the participants of today's study, the benchmark study. So we selected the 3 spaces that we had access to, specifically both versions of Freedom Space and Inmin Real Space, the newest release. All of the 3 spaces, they were used in the Synton-based format. And you can see the parameters as well. So first, to start working with the spaces within the RDKit Synton-based search, you have to load them. And you can do it in 2 different ways. First, you can load it using the txt Synton file. The ones that we provide or Inamin provides are 100% compatible with the search, so you can just use those if you have them. Another way to do that is to use the specified binary SPC file that works within the search algorithm. Here we are looking at the benchmarks of the RAM usage and time needed to load this SPC file into the memory. You can see that the numbers are very reasonable and it can actually be performed even on a simple computer, like nothing very fancy. And here, we see something not very logical, that even though Freedom 4 is much bigger than in Real, it's twice bigger, but the size of the RAM usage and the time is actually smaller. And you'll ask why this is the case. And the reason for that is that Inamin Real has much more sub-reactions. So they divide their reactions into additional splits so that they can account for the price of different building blocks and some reaction compatibility. So this is why their space has this many sub-reactions, which results in duplicated syntons and a harder structure. So this is why this affects the loading time, and also you'll see later that it will affect the search time as well. The second thing we did is we performed different kinds of searches, and here we tested several parameters. I'm going to slightly talk about them. So on the x-axis, you can see the number of threads. So this is a parameter that you can input into the search to make it faster, as you understand. And we tested the search times for different spaces on a different number of threads, so you can see the performance. And also each search for each molecule was repeated 5 times to account for reproducibility. But I do have to say that the sizes of the sets we used are rather small because this already took quite a bit of time to compute. So and we just kind of wanted to give a ballpark of the times that it's taken. So if we're speaking about substructure search, you can see that the times needed to perform that are actually very, very small, especially knowing the sizes of the spaces. And we can see that for Inamin Real, because of their harder structure, it takes more time, though it's kind of not very important because it's still very, very fast. If we move to similarity search, here we perform two additional tests with two kinds of fingerprints. And you can see that the similarity search logically is slightly longer, though if we're looking at a single thread, it's somewhere around 7-8 seconds for freedom space, which is again a very reasonable time on not a very, it's an okay processor, but I mean, it's not like a cluster or anything. And then if we also compared the similarity searches in different spaces. And again, you can see for in real, there's quite a nice curve of how the search benefits from threading because it's longer and you can see it better. But overall, it's still very reasonable and we recommend it for everybody who would like to try it out on their own. And the fourth and the final benchmark that we did was actually kind of handmade stuff, because when we started working with the started working on the Freedom Search platform, the sentence-based search didn't have exact match, and I think it still doesn't. And we really needed exact match because we needed to return the ID for the molecule that comes as a query to process the order, for example. So we created kind of the makeshift exact match on top of the substructure, and we did it in two steps. So first, the search is performed, first the so-called fast search is performed with the limited number of hits of 1,000. That runs almost instantly. And we noticed that and we noticed that most of the top performing results that are likely exact matches, they will be found within the first few results returned by the algorithm. So this is how we sort out the easy queries. But then if we see that there is more hits available and we still haven't found our exact match, the search falls into the deep search, which increases the number of hits that are explored by the algorithm. And then we can check kind of more thoroughly if it is present. Yeah. So this graph was done for 1,000 compounds. And we're happy to say that all 1,000 were found actually using the exact match search because they should be there and they are there. So it works pretty well as well. And you can see that on the right to the tens of seconds, those are the times for the deep searches, and the ones that are located closer to 0 are the times for the fast searches. Okay, and with that, I would like to acknowledge the work of some great people who participated in this presentation. First, I want to thank my colleagues at ChemSpace who are actually watching this right now online, probably, and our CEO, Olga, for her constant support. I also want to thank Yuri Moroz, from Inamin, who always helps us with our ideas and implementations. I also want to thank David Cosgrove, who was the implementer behind the Arctic Synthon-based search and also participated in benchmarking. And also, I would like to thank the Armed Forces of Ukraine who are protecting our country during such hard times so that we can continue our work. Thank you so much, and I will be happy to answer questions if you have any. Sorry?
Okay. Questions? There's one in the back, Thomas.
Okay.
Are they all deliverable in 6 weeks?
So actually for real space, oh, I'm very sorry. So the question is, the 77 billion and 142 billion, are they deliverable within the 6 weeks? So for Idiom and Real, their lead time is actually 3 to 4, because all their building blocks are in stock, so they don't have to ship stuff anywhere. For Freedom Space, the lead time is 5 to 6 weeks, because we need to buy the compounds from other vendors and ship that to the synthetic facility, so that's why it's longer. 7 million. So you might be talking about the general in-stock catalog, right? Yes, the 7 million, they are in stock, so they're available off the shelf, and these are make on demand. So if you would like several compounds from there, you just order and they're made for you.
I'm curious, when you were doing the models to predict whether or not the building blocks will work in a reaction. And if you tried doing a multitask model, for example, for all of the amine reactions.
So the question is how we try doing the multitask models for the same type of reaction. And actually we haven't. I have thought about that, but we're still looking into the fact that even though the amine reactions are technically, for example, amide formations, but they're still performed within a different reaction protocol. And I'm not sure how that will work out, but this is something that we actually wanted to try along with another idea that we have in terms of improvement is to add additional features like reaction-based features, for example, for specific reagents, because currently this operates only on the graph representation without additional features.
Yeah, it's funny.
Start analyzing the common track for models. People bundle react a onto
So you're asking how we analyze the importance of specific substructures within the building blocks, right? I'm sorry, I cannot hear what you're saying. Yeah. Yeah. Yeah, I just don't hear you very well. I'm sorry.
I wondered whether you can overlook your chemical models and find out which fractal model they found out.
So actually, this is also something that we're currently doing. So there are some setups for kind of explainability analysis within CampRop, and we're looking into that. Currently, what we have analyzed is we have performed numerous overlaps of chemical spaces between different building blocks to see how they overlap and can we actually use the models on external building blocks, because if they're super not similar, the performance is going to be much worse. But yeah, this is some work in progress. I'm not sure if it's going to be published within the next paper, but if we get something meaningful, we'll definitely show that to the community. Thank you so much.